Assalamu alaikum wa rahmatullahi wa barakatuh. I realized that since a lot of viewers on this video, or like my future videos, might not know me, my name is Alex and I am in year 13 of A levels. But before I go through this video and start it off, I wanted to show you, look how beautiful this location is, Allahumma barik. And also, guess what? I found a whiteboard, so I can actually show you my working out properly. And I flipped my video, which is really strange because I saw the flipped version. I did a test recording, and I look so different. But yeah, I'm ready to start the video, and as you remember, it is one take only because we allow mistakes in this life. So yeah. Oh wait, I need a whiteboard pen. I just realized that if I don't have a whiteboard pen, then I can't actually draw anything. Alhamdulillah, there's a whiteboard pen. Okay, but do I have a... Yes, and I have a cloth to rub it out. Okay, so my laptop is actually dead right now, so I'm charging it. And my phone is on 16%. So, and there's no charging port here on the desk. There's only one on the floor that I'm connected to, which is an issue because that means I'm gonna have to keep swapping the charging cable every few, like 15 minutes or whatever. Anyways, let's get started. Yeah, I love how peaceful it is, by the way. It's completely silent. I'm on here on my own. And alhamdulillah, there's the sunshine over there. And it looks so beautiful, honestly. I'm gonna show you the sun shining. Look. How peaceful it is. Oh my days. Yeah, this is all live. I mean, not live, but like raw, uncut audio, uncut video. And I can't believe I'm publishing this without editing or even looking at the video before I send it. I hope I don't say anything like inappropriate or you know, cancellation worthy. Okay, I should get started, otherwise this will never end. Let me get my stuff from my bag. I'll be back soon. I just got the many books that I have here. This is really heavy, by the way. It's like at least 3 kilograms, I think. Yeah, my bag is like 10 kg. It's absolutely insane. Alright, gonna turn my laptop on. Today was a busy day, man. If I check how much sleep I got 6.5 hours of sleep, as you can see there. And I've been doing that for weeks upon weeks now. And I'm barely surviving. I'm literally a zombie at this moment. Okay. My laptop is open. So I have too many tabs open. Okay. Which lesson was first? Time to find out, because I do not remember my timetable. I had physics first. Okay. Oh, in physics we had our radioactivity assessment. So, you know, it didn't go that well, but it was alright. Let's actually do some questions now. This is exciting. Okay. Because the thing is, I'm really bad at physics, so you're gonna see like how bad I am firsthand. Also, I'm speaking quietly because like I'm just so tired. I don't like to shout or speak loudly. Nuclear binding energy. Interesting. Right. This has a mark scheme. Let's go. Okay. Alright, awesome. Let's do these questions. Okay. Binding energy. In the context of an atomic nucleus, state what is meant by binding energy and explain how it arises. So, binding energy is the amount of energy required to separate a nucleus into nucleons, into its separate nucleons. So for example, if you had, okay, let's move on to the next question first, and then I'll actually explain, because this is actually a very interesting concept that I had to ask my classmate for help on. State what is meant by mass difference. So mass difference is, or also known as mass defect, is the difference in mass of the nucleons separately and when they're together, so as a nucleus. Let me just write that down, the difference in mass of the nucleus and the nucleons when they're separated. By the way, these might not be right answers. So, and the relationship between binding energy and mass difference. Okay, time to explain. Let me get a whiteboard. Alright, cool. Firstly, I'm going to rub out whatever this is over here. Okay. Also, you know how the videos flip? That means this probably looks like my right hand, right? Oh, it does. And this is my left hand. Wait. Oh, if it's flipped, that means it's normal. But in the video, it looks like this is my right hand, but it's my left hand. Okay, anyways. So, so we have a nucleus here. Let's just say that's 2 protons and 1 neutron. Does that element even exist? I'm not sure. Let's say 2 neutrons and 1 proton. That is hydrogen 2. Does that even exist? Maybe. H31. That's what it looked like. 3 because that's a mass number. 2 protons plus 1. 2 neutrons plus 1 proton, and then 1. That's the proton number. Okay. So you can have it as a nucleus, or you can have the nucleons separately. And then the mass difference is the difference in mass of this as a nucleus, and the difference, the difference between this mass of the nucleus and these 3 nucleons separately. So, for example, if we were supposed to group these and call it M2, and group these and call it M1, so the mass of the nucleus and the nucleons on there separated as a different mass, you'd expect these to have the same mass, like I did, but no. There is a difference in mass, okay? Because mass is literally just energy. E equals mc squared. Energy is mass times the speed of light squared. So you can interchange mass and energy. Alright, so in this case, actually it depends. You can't say M1 is greater than M2 or M2 is greater than M1, because we have, if we draw a graph of binding energy per nucleon, it would actually look like this, where iron, Fe, is at the top of the stability curve, which means it has the greatest binding energy per nucleon. And that's what makes it most stable, because you need the most energy per nucleon it has to actually separate it out into its constituent nucleons. So in this interval over here, you'll have fusion, but in this interval over here, you'll have fission. And that is because, I'm like learning this as I watch this, okay? So if you start with an atom over here, it starts off with a low binding energy. So you want to fuse it with other atoms or other elements, well, it doesn't have to be other elements, but other atoms, let's say, to move it to a higher binding energy. Do we actually though? I should probably check that. Yeah, that's what I wrote on my diagram. That's probably what. Fusion is more efficient as it has a greater amount of nucleons. I think that's what happens. We should definitely watch a different physics video because I'm not the best at explaining this. And I could be completely wrong when saying this. So fusion, we want to get to a higher binding energy. Why? Shouldn't it be to a lower binding energy? Because if you're starting with an atom, right, and you do fission, you want it to go to a lower binding energy. So that means you have that energy difference. Huh? What? Oh my. If only Zihan was here or some like other classmate of mine who's a lot better at me than physics. Better than me at physics. Oh no. Okay. Why is fusion? I'm gonna search that up, see if I can find an answer. Because why does fusion add low? What? I can't find the answer online. Well, not straight away anyway. So, small nucleus. By the way, this is binding energy per nucleon. And this is atomic number or atomic mass. So over here you'll have like uranium or whatever. When we're fusing, we're going from an atom with a low binding energy and a low atomic mass to an atom with a higher binding energy and a greater atomic mass. So why does that create energy? Okay. Wait a second. So this mass is smaller than this mass. Let's go through a question. I think the best way to go through this is with an actual question. So I have my worksheet here, by the way. And we're going to go through the questions and see if we can actually uncover what is happening over here. So state the relationship between binding energy and mass difference. So mass difference is, as we explained, the difference in mass of the nucleon and its nucleon separated. And then the binding energy is the mass difference converted to energy. Because it's the difference in mass. Because we have the same amount of parts in here. So it should be proportional. Binding energy. Wait, but it doesn't want me to say so binding energy is just the energy equivalent of the mass difference. It sounds right, but whenever I write an answer, I always get it wrong. I don't know why. Calculate the average of okay, let's check our answers. Alright. The energy required to break nucleus up into separate nucleons. Did we write that? Yes. Okay. Well, why did I think that was wrong? Okay. And then mass difference is the difference in mass between the mass of the nucleus and the total mass of the nucleons. We wrote that. And then the relationship is E equals mc squared. Which I did not write, but I was technically correct. Okay, that's 2 out of 4 marks there. E equals mc squared, which is literally what I said earlier. And then we also need another mark. Work is done on nucleons by the strong force. Energy associated with the strong force. The energy required to break the nucleus up into separate nucleons is associated with the strong force. And that's because the strong force is the thing that's pulling everything together. So the neutrons provide the strong force while the protons provide the electrostatic force. The mass of the nucleus is smaller than the mass of the constituent nucleons. Okay. Okay. So it looks like I was wrong here. It looks like M1 is always smaller than M2. Do you know why? It's because you need energy to break up M1 and turn it into M2, which means M2 is equal to M1 plus whatever energy, which means M2 is greater than M1. And energy is the binding energy, the energy required to split up the nucleus into its constituent neutrons. Nucleons. Yeah, okay. So let's explain that. That's awesome. Okay, we're going to go through that question later on. Next one. Calculate the average binding energy per nucleon in MeV for a nucleon. It says a nucleon minus 1. Wait, let me just check I have enough battery. I have 9%. Okay, that should be fine for a bit. For a nucleon of zinc nucleus, which is 6430 Zn. Okay, let's start again. Rob. My sheet of paper flew away. Okay, so we have 64 Zn 30. Let me get my calculator. The average binding energy per nucleon in MeV of the zinc nucleus. So to work out the binding energy, do you remember what we need? We need the mass deficit, or the difference in mass, between the nucleon and its neutrons when they're separated. Okay, so we have the mass of the atom already, which is mass atom 63.92915 U. U is a constant. Let me get the formula book real quick. Physics formula AQA. U is equal to an atomic mass unit equal to 931.5 MeV. Okay, so now we have the mass of the atom. We need to work out the mass of the neutrons when they're separated. So separated mass separated equals. How do we work out how many protons there are? Use the proton number. 30 times mass of a proton, which is 1.00728 U, plus how many neutrons are there? Well, we do the atomic mass number, take away the proton number, which gives us 64, take away 30, 34. So 34 times mass of a neutron, 1.00867 U. Oh, we need to do mass of electron too. The mass of an electron is 0.00055 U. I don't even know if that's necessary or not, but we will do it anyway. Plus 30. Oh yeah. Do you know why there's the same amount of electrons as protons? Apart from in ions, of course. It's because all atoms are neutral. And why are they neutral, naturally? It's because if they're charged, then they're going to want to take the electron from somewhere else, or give their excess electrons to another atom, because they like to be stable, just like the stable gases. Okay, 30 times 0.00055 U, which is, let's work that out. 30 times 1.0728 plus 34 times 1.067 plus 30 times, that's 34, yeah, I wrote that, 0.0055 is 64. Should it be 64? Yeah, it should be 64. 64.52968 U. And I'm not talking about U, I'm talking about the atomic mass unit. Just so you know, Okay, so now that we have the mass of the atom and the mass of them when they're separated, now we need to work out the difference between them. So take them away from each other. 64.5, take away 63.9. Take away 60.9, 2.15, gives you 0.60053 atomic mass units. Now we need to convert that into energy. Dude, this is so easy. It's 5 marks. Dude, when is physics this easy? It's never this easy. Okay, so an atomic mass unit is 931.5. So literally just time this. Energy equals, or binding energy equals 0.60053 times 931.5. Yeah? Times 931.5 equals 559.39 MeV. And is that our answer? 5539. Let me just write that down. 5539. 559.3. No. 9 MeV. Oh, sorry. Per nucleon. We haven't actually got the answer yet. So, this is the total binding energy required to split up the nucleus into its constituent nucleons. But we want the binding energy per nucleon. So guess what we do? Divide it by 64, which gets us 8.74. So let me write that down. 8.74 MeV. Okay, that's the answer to that. Why would you expect the zinc nucleus to be very stable? Because why? Well, we know that to be a stable atom on that binding curve that we showed before, you need to be at quite the top of the binding curve, because then you need the most amount of binding energy per nucleon to actually split the nucleus into the nucleons. So I assume that because the binding energy per nucleon is so high, by the way, the graphs look something like this. That's 0 to, I think that's like 10. And then, let me just check. Binding energy per nucleon graph. Dude, that's so cool. Okay, that's something to remember. This is 9, and it never touches 9. And we just worked out the binding energy per nucleon for zinc is 8.74, which means it's somewhere at the top of the stability curve. Well, it's not actually a stability curve. It's the binding energy per nucleon graph. So that's why the zinc nucleus has to be very stable. The binding energy per nucleon is very high. and compared to other elements. So is harder to break up. Split it into nucleons. Okay, let's check our answers now. .74, obviously. Okay, that's 5 marks. And then the second part, nucleus has a high value of binding energy per nucleon, and that's what we put. Awesome. Or you could also put it's near the maximum of the binding energy per nucleon curve. Over A. What is A? Atomic mass. Okay. Alright, next question. Calculate the binding energy of a nucleus of cobalt 5927. Cobalt 5927. Nice. Cobalt 5927. Get that. Trying to find. It doesn't. That's strange. It doesn't give the mass of the protons or electrons in this question. But in the formula book, it also doesn't give it. It gives the mass. It gives the rest energy of them. Can we calculate it just using the rest energy? We probably can, you know. Let's do that. Okay, this is a different question. Let's run everything. So, the mass of 59CO27. The mass of the atom is 58.9330. 58.9330 U. And we know that the energy equivalent of this, so turn it into energy, equals times 931.5. 58.9330 is 54,896.2758 MeV. We know that this, added with some binding energy, so 96.2758 plus let's call the binding energy X. No, that's a stupid thing. Just call it EB. Equals the energy of the electrons plus the total energy of the electrons, protons, and neutrons. Wait a second. It's nucleus. Why do you need the mass of the electron? What? Oh, okay. So in the previous question, it says that's the mass of the atom. So that's why we needed the electron. But now this is the mass of the nucleus on its own. So we don't need the electrons. So it's just 27 times the energy of a proton, 98.257, plus the difference between these two numbers, which is 32, times the energy of a neutron, 939.551. So EB equals, and then you take them away, and that should be the answer. 25 plus 32 times 939.551. If you think about it, the reason like M1 is smaller than M2 as we did before, is because if the nucleus had less energy, wait a second. The nucleus has less energy. Okay. If the nucleus had more energy than the particles when they're on their own, then it would just love to split up all the time and then like create infinite energy. So I assume that's why that doesn't happen. Anyways, let's do this question. Fine. 0.275. We get a value of 502.1062. Does it want it per nucleon? No, it doesn't. So that's our answer. Let's check that real quick. 503.8. Bruh. Is there rounding error? Dude, it got the mass in U out of nowhere. What? Data may come from rest mass, which is what we did. What? Bro. What is going on, bro? I need to get some food. This is too much thinking for me. So let's see. If I calculate it using U, which is 58.9332, take away 27 times. We're using the. So right now, instead of using the rest energy of the protons and the neutrons, I'm going to use the U value, the atomic mass unit value. Okay. Because I genuinely think it's just a formula book error, and it's not my calculation error, because all my working is correct, bro. So let's see. I'm going to sit down. Take away 37. No. What is it? 27. Take away 27 times. What is that? 27 protons. I got a negative number. What did I do? Bro, what did I do? Oh, yeah, I'm supposed to get a negative number. Okay. 0.5, because I subtracted them the opposite way around, so of course you're going to get a negative. 0.548 times 931.5. Yes, literally just, they used the atomic mass unit, which is not given in the formula book. I don't know why they're using that. They got that out of nowhere, bro. Anyways, they used that value, so they got that answer, but I think our answer is also correct. Let me write that down. 502.1062. Okay. A nucleus of iron. We're going to do this question now. Have a look at it and pause the video. A nucleus of iron Fe59 decays into a stable nucleus of cobalt. Decays by the total energy released. Calculate the maximum possible kinetic energy of the beta minus particle emitted. Oh wait, I need to charge my... Dude, I need to charge my phone. Okay, I realized that, bro. Otherwise the video would have just cut off like that. Okay. Total energy released. Let me get some water. And it's 2 marks, which means we need to do some sort of calculation. Interesting. You know, I'm confused now. Because we have 3 lines here. 3 lines with beta minus particles going to each one of them. But how about the ground state? Why does that not have a beta minus particle? Maybe because if the beta minus particle, if you go to the ground state, then the beta minus particle is not, it's not even in the cobalt nucleus anymore. That's energy. Okay. In the question it says, calculate maximum possible kinetic energy of the beta minus particle when the ion nucleus decays into an excited state that has energy above the ground state. So the beta minus particle has to be above ground state for the question to be valid. So I really have no idea for this one. It should be 2.52 take away 1.76, which is the energy level right above. So that should be 0.76. Oh, that's where the second marks come from. 0.76 times 10 to the minus 13 joules. And then convert that to MeV by multiplying by... What do we multiply? Magnitude of the charge of the electron. No, right? Where's EV, bro? What do you have to use? Magnitude of the charge. So we have something to the power of minus 13 right now. But the magnitude of the charge of an electron is to the power of minus 19. Okay, let's just divide by that. That's probably all you have to do. So I'm overthinking things. 0.76 times 10 to the minus 13. I'm going to write this on the whiteboard. I should put this here. No, I can't put that there. Anyways. So, we have (0.76 times 10 to the power of minus 13 joules, and we want to convert that into MeV, which is literally just EV to the power of, what's million? There's kilo EV, so that's probably times 10 to the 6. So to do that, we just divide this by the magnitude of an electron, or the charge of an electron, sorry. The magnitude of the charge of an electron, which is 1.6 times 10 to the minus 19. 1.6 times 10 to the minus 19. And when you do that, you get 1.6 minus 475,000 eV, which is the same as 475 kilo electron volts or 0.475 mega electron volts. So that should be the answer. Inshallah, bro. Inshallah. Otherwise, oh my days. Let's see. What question even are we on? 2B. Let's go. We got it right. Alhamdulillah. Okay. Following the production of excited, state the maximum number of discrete wavelengths that could be emitted. Following the production of excited states. The maximum number of discrete wavelengths that could be emitted. Okay. So it could, when the iron nucleus decays into a cobalt nucleus, it can go into one of three excited states. It can go to the highest energy level, the second highest energy level, and the third highest energy level corresponding here. That means 3 different wavelengths, because if you have 3 different energy levels, when you're emitting gamma radiation, and you're doing this, by the way, gamma radiation is literally just a photon, I think. Correct me if I'm wrong, or maybe don't, if you're not watching this video. So gamma radiation is just a photon, and photon is just a packet of energy. So the higher the energy, the greater the wavelength required to have the same energy with that single photon. So we have 3 different discrete wavelengths that could be emitted of gamma radiation. Calculate the longest wavelength of the emitted gamma radiation. Now that's annoying. Oh. Okay. Do you know what we're going to do here? So we need to work out the energy of this gamma radiation, and then when you convert into wavelength, using E equals HF or something like that. So we're starting with 2.52. Okay, let's write this down. Let's write this down. Okay, so we're starting from Fe59, and we're going down, emitting beta minus radiation, B, which is strange. Are we actually emitting that? Yeah, we're not emitting that. Or are we? I don't even know. I don't even know. What? Yeah, it's emitted. So what is this? What is this? What is this? I don't know. Whatever. So it's starting at a energy level of 2.52 times 10 to the minus 13 joules. And we're going to the highest energy level. There's one here and there's one here, remember? But we want the smallest amount of energy, because longest wavelength has the smallest amount of energy. Don't ask me why, you should already know. I'm not teaching you guys, I'm teaching myself because I struggle at this stuff. Okay, let's calculate the difference in energy between this. Difference in energy here is 2.52 take away 2.29, which is 0.23 times 10 to the minus 13 joules. Okay, so now that we have the energy, we want to use the equation E equals HF to work out the frequency of the photon. It's only a 3-mark question, so it's not too complicated. We need to divide by H, which is Planck's constant. Last time I mixed H with like momentum or something like that, Planck constant. So we're dividing this by Planck's constant. And we're working with joules, I'm pretty sure. Yeah, because Planck's constant is in the units joules per second. while this is in the units joules. Wait a second. Yeah, we're dividing by joules. Okay, let me show you this, guys. So the reason I was confused is because if we multiply energy by Planck's constant, we'll be getting joules squared S. But instead, we're getting the unit, so E over H equals F. I just rearranged this equation above. And we have, if we use the units form of this, energy is joules over Planck's constant, which is Js. Joules per second. Joules seconds, sorry. Equals F, which is frequency is 1 over S. S minus 1. Frequency is how many revolutions there are per second, right? Yeah. And then time period is in seconds because T equals 1 over F, which is S, or 1 over S minus 1, which is S. Awesome, man. Awesome. Okay, we didn't actually work out the answer to that question because, let's just do that. 0.23 times 10 to the minus 13 divided by Planck's constant, which is 6.63 times 10 to the minus 34, which is 3.469, or just 3.47 times 10 to the 19 meters. Dude, that does not sound right. Let's check it though. Yeah, it's wrong. Oh no, what did I do? Dude, 6? What are you on about? There are 6 discrete wavelengths that could be emitted. But why? Why is the question? Why? How to work out? No. You know, it's so hard to revise on your own when you don't have something to follow. Okay, I'm gonna go and save my exams for radiation. Radiation, save my exams. Save radiation, use radiation, binding energy. Okay. Let's see what save my exams says. I'm gonna try not to make an S here. The gradient is much steeper for nuclei at the start of the binding energy per nucleon curve, which is why they release a greater binding energy than fission reactions, which are on the other end of the binding energy per neutron curve. Okay, that's not what I want to know. Mass difference in binding. Dude, this is so long. Radioactive decay, I think that's what we want to know. Applications, radioactive decay. Dude, the question's not here. How am I supposed to do the question if I can't even find... Dude, I literally have Bro, come on. I literally can't do the question because I don't understand it. That's really sad, man. It's really sad. Okay, I found it. Okay, I found the exact question. There are 6 possible transitions. Okay, I found it. I found the answer, guys. I found the answer. So we have 3 different energy states there. And then we have the ground state. So for gamma emission to be emitted, gamma radiation, sorry, you're only releasing energy. You're not actually releasing any particles. Well, a photon, I don't think so have a particle. Let's just not think about that right now. You need to release different amounts of energy. So this electron could come over here, or this electron could come over here, or the electron could come over here. That's already three discrete wavelengths that could be emitted. Or a wavelength here could come all the way over here, or it could come over here. Or an electron here could come over here. And that's 6 wavelengths, 6 different discrete wavelengths of gamma radiation. And then why did I get the next one wrong? Calculate the longest wavelength. The longest wavelengths, the longest wavelengths is from here to here, which is 2.29 take away. The value here is 1.76. Wait, no. Ground state. The longest wavelength. Oh, the longest wavelength is what? The one with the lowest energy. Okay. So if this is 2.06 and this is 1.76, what's the difference between these? Difference between these is 0.30. Difference between these is 0.23. So we're going to use this one, 0.23. Dude, that's what we used. Wait, I was just doing something one. Yeah, so 0.23 E equals HC. Oh my days! I worked out frequency. Look, that's frequency. Let me just check if the equation for thing is in the formula book. It's in the formula. I just used the wrong formula, okay? I just used the wrong formula. HC over lambda. E equals HF, or you could do HC. C is the velocity of the wave over lambda wavelength. Plug that in. So 0.23 times 10 to the minus 13. Okay, no, sorry. HC. H is 6.63 times 10 to the minus 34. Multiplied by the speed of light. Where are you, bro? 3 times 10 to the 8. Divided by 0.23 times 10 to the minus 13. And that gets you the answer. Oh, man. Yeah. Okay. Awesome. Let's go. Finally. So glad to have saved my exams for real. That's 6. How many questions are left? Still have questions. In the series of the game, calculator. Oh, this is an easy one. Oh, that's why it's 1 mark. Got me excited then. I'm gonna turn the light on. Does that look better? Maybe. I could literally be here all day teaching myself. Right. So we're starting with an isotope of uranium. And it's decaying into a stable isotope of lead, which is 20682. 20682 Pb. Alright, this is light work. So do you know how much an alpha particle is made up of? So A, and then XY. What are XY in this case? So X is the number of nucleons and Y is the number of protons. But I just call these random, I assigned any letters to these variables, so these aren't actually X, that's not actually Y, that's A and Z, but don't worry about that. So in this case, X is 4 and Y is 2, because 2 protons, 2 neutrons. An alpha particle is made up of 2 neutrons and 2 protons. Cool. That's an alpha particle. So it says in the question that it decays, alpha decay occurs 8 times, which means there's 8 times 4 to alpha. So we have 8 times 4, 32. 32 plus 206 does get us 238. But 8 times 2 plus 82, so 82 plus 16 is 98, which is 6 more than we need here. So it says beta minus decay occurs n times. So we're adding n times beta minus. So beta minus 1, 0. But how do we know that beta minus 1, why is there minus 1 there? I thought beta minus was just like that. So why has the minus gone here? Let's think about what actually happens in beta minus decay. So beta minus decay is when a neutron, is it when a neutron turns into a proton, or is it the other way around? So when a neutron turns into a proton, it also needs to emit a negative particle, which would be an electron, wouldn't it? Which means it would be anti-neutrino. So if a proton went into a neutron, to balance that out, you would need a positive particle, which means it will be beta plus. Plus an electron neutrino. Okay. Beta minus, because we need to cancel out, we need to balance the charges on both sides. So this is the decay that we need. A neutron is decaying into a proton and emitting a nuclear electron. A nuclear electron because it's coming from the nucleus. And then this is beta plus decay, which we don't need to worry about, where proton turns into a neutron and then a positron is emitted. And then to know whether it's an anti-neutrino or neutrino, you need to check whether the electron-lepton numbers match. So beta minus, well, electrons are normally negatively charged, so that's +1 electron number. And then antiparticle, we need a -1 electron number to cancel that out on both sides. Because that's a 0 lepton number, +1, -1. Here, 0, 0, -1, +1. Why is it -1 when there's a positive? Is because an electron is normally negatively charged. So if we make it the antiparticle of an electron, that means it has a -1 electron-lepton number. And the lepton numbers for electrons has to be the same on both sides. And that's how we balance these equations. So now that we've justified why it's -1 on the proton number, dude, is it -1 on the proton number? I'm so, what? Sorry, I'm going crazy right now. Beta minus decay is when a neutron turns into a proton. No, but I don't understand what's going on. Oh my days. But in beta minus decay, you're gaining a proton. Dude, what's going on, man? What's going on? Okay, let's do an example. Let's start with an alpha particle. Let's say we decay via beta minus. So this will go to, so beta minus, remember, neutron turns into a proton, which means the new particle has 4 nucleons but 3 protons. Let's call that X. Plus beta minus, and then plus an anti-neutrino. Let's just turn that to, so yeah, that works out. What am I not understanding here? Oh, so this is -1 for the proton number. So it looks like you're actually removing a proton, but no, you're adding it on here. So yeah, all balances out. Everything we did here was correct. So we have 96 here because we're doing 82 plus 16, which is 98, sorry. 98 take away 92 is 6. That means we need n equals 6. And that should be the answer. And that is a 1-mark question. Wow, well done, Alex. Well done. I swear. Dude, this video is already 1 hour long. It's absolutely insane. Yeah. N equals 6. I think. Yeah. Alright. Next question. Explain what is meant by the binding energy of a nucleus. Yeah, let's go. We got a repeated question. So, do you guys know what binding energy of a nucleus is? It's the energy required to split up a nucleus into neutrons, into nucleons. Energy required to split nucleus into nucleons. Sorry. But it says to explain. We can also say total mass of nucleus is smaller than total mass of nucleons. But where did the 2 marks come from? That's my question. Energy required to split up nucleus, yep, into individual protons and neutrons. Cool. Awesome. That's 2 marks. Okay, use figure 1 to estimate the binding energy of the 9. We're doing this question, by the way. To estimate the binding energy of the 206A2 Pb lead nucleus. Pb 82206 nucleon number. But come on, this is easy. Okay, that's why it's 1 mark. So literally just read from the graph. We know it has a nucleon number of 206, so just read 206 is here. 7 point, the hard thing is reading from this, 7.88, let's say. 7.88. Let's go to the next questions. Sketch on figure 2, graphs to show how the number of atoms vary over a period of 1 times 10 to the 10. Okay, light work. we know the half-life is 4.5 times 10 to the 9. So, if it starts... Dude, this was the question on my radioactivity test today. Okay, let me just... Oh, that means I can literally check if I got the question right or wrong. That's so cool. Okay. At 4.5 years... At 4.5 times 10 to the 9 years... Wait a second. This entire question was on my radioactivity end of topic test. I should have done it. Should have done it before the test, man. Okay, anyways. At 4.5 years, it will have halved, so it'll be at 1.5. 1.5 in 4.5 years. And then at 9 years, at 9 times 10 to the 9, it will be at 0.75. Because it's halving again. So the final graph would be like this. Be like that. Where uranium is one decreasing and lead is one increasing. Because uranium is decaying into lead. Okay, that's that question. Let's check it. No. Inverted graph, cross out, yeah, 1620, where did that come from? What? Side, that was, okay, so this one's correct, and this one is wrong. Do you know why? Because this is the binding energy per nucleon, and we read that. But it wants the total energy of the nucleus, so you just need to multiply by the number of nucleons, which is 206. So 7.88 times 206 gives us 1,600, which is our answer. 206. Nice. Okay. Last question, for physics anyway. A certain time after its formation. So originally, the sample contained 3.0. Let's wipe this all off, by the way. I hope you could see what I was doing by then. I hope I wasn't covering it up. 3.0. Originally, it contained 3.0 times 10 to the 22. And then, after, like, however many years, it decreased to 2.0 times 10 to the 22. And this is uranium, while the other is 1.0 times 10. Pb, lead. So it's originally all uranium. Now, it's decayed into 1 part lead and 2 parts uranium. So it wants us to show that the number of atoms in the rock sample. Well, I already gave you guys the answer. Did someone knock on my door? I don't think so. I hope not. Anyways. So, a certain time after its formation, the sample contained twice as much uranium as lead. And you have to show that the number of atoms of uranium, in that case, would be 2.0 times 10 to the 22. And it's literally just a ratio of 2 to 1. And you're starting with 3, so 3 divided by 3 is 1. 3.0 times 10 to the 22 divided by 3 is 1.0 times 10 to the 22. So you do 2 times 1.0 times 10 to the 22 to give you 2.0 times 7 to the 22. And that's your answer, bro. It's 1 mark. I don't understand what show that they even want. And then calculate T in years. So this one was kind of a strange one. So I forgot the equation in the exam. So I'm not sure if I'll get the method marks for it, but I actually got the right answer. Because if you think about it, 3.0 times 10 to the 22, we're multiplying by half-life. So the half-life equation is a half multiplied by however many half-lives. So let's say the total number of time in years over the half-life. and then that gets you your final value after however many years. And the final value was 2.0 times 10 to the 22. So we just rearrange on both sides, 1/2, and then we already know the length of a half-life, which is 4.5 years. So let's do 4.5 equals 2/3, and then log 0.5. Or we just do ln, why not? Ln half equals ln 2/3. T equals 4.5 times ln 2/3 divided by ln 1/2. And that should give you your answer. I didn't write it like that exactly, so I'm not sure if that will give the same answer that I got in the exam, but we'll find out. 2.63, that's the same answer that I got. But is that the correct answer though? And it is. Nice. Ah, cool. They used pretty much the same thing as me. Not the exact same, but... So they used this equation, let me show you. They use that, but instead it equals 3 times 10 to the 12. What? It's not 12, it's 22. Yeah, I just read that wrong. 22 times e to the minus... That's just weird. Like, why is it e? I don't understand that. Like, where is the half coming from? Because it's half-life. What did... I don't know what that means. I don't understand what that means. Like, this needs to be arranged to the same as that. So that means e to the minus that equals a half t over... I don't know how. How? If we ln both sides, we get minus ln half. Well, what can we do here? Divide by t and multiply over. Y squared equals ln. Huh? What do we get with ln 2? ln a half is negative. Okay. So that doesn't make sense. How can the half-life be a constant if the half-life is what's defined in the question? Yeah, that's why I don't like that equation, guys. This is the equation you guys should use. Multiply by half to the power of t over lambda. I was telling my physics teacher this and he was like, what heresy is this? Alright, that's physics done. I'm going to stick that in now. I'm going to stick that in, and now we're going to move to our second lesson. I have another worksheet here, which is to do with radiation. Let me see if any of these were on my test. Alhamdulillah, they weren't on my test. Oh, good. Otherwise I'd be very angry. We can do that next lesson. Okay, that's physics. Now, what was my next lesson? Let's find out. My next lesson was... Oh, yeah, I had a double third math lesson. Let's go over the rest of the methods of differences. questions because I really want to do this. Okay. So I have a problem, okay? And I really need you guys to help me with it. The problem is, I can't do simple algebraic manipulation. I can't simplify this equation. I got it wrong for whatever reason. I was doing so well. I was literally getting every question right, and that never happens in further maths, okay? In further maths, expect to get every question at least slightly wrong. Right. I'm gonna put this charger away. I don't need it. Dude, what is... Okay. Is there a bin here? There's no bin here. That's crazy. Right. I'm gonna put this charger away. There is a bin here, never mind. Alright, so what I wanted to say was that there's this question where I did most of the working out. I literally got the final answer, but I just can't simplify the end. So I got 5/3. I'm so glad that wipes off so well, you know? Right. 5/3 minus 4/9 minus, is that it? 3. Let me just check that's correct before I do a load of simplification for no reason. 8. Four over 9n plus 3, yeah? And then 4/9n plus 12. Okay. Yeah, right. So this simplifies to a, and I'm going to try to do this as fast as possible. No, n plus b over okay, that's what it simplifies to. Alright, how do we start? Okay. 5, 9n plus 12, 9n plus 3, 3, 9n plus 12, 9n plus 3, minus 4, 9n plus 3, 3, minus 4, 3, 9n plus 12. Okay, expanded that out. Now we need... Oh, this is a nice lot of expansion. 81n squared plus... I'm gonna have to use a calculator for this. Plus 135n plus 36 minus 12 plus 3 minus 12 9 9n plus 12 9n plus 3 equals 405n squared plus 675n plus 180 t minus 108n minus 36 minus 108n minus 3. By the way, let's just turn that into a 27 and then take the 3's out of here because they're bothering me. Like that. Okay. Can you see that in the video? Yeah. We're just collecting like terms now. 405n squared. So 675 minus 108 minus 108. 4 plus 459n. 180 minus 144 minus 86. Cancels out. Let's go. That's what's supposed to happen. 3n plus 4. 3n plus 1. So does that divide by 27? Yes. 459 divided by 27? Yes. Equals 15n squared plus 17n all over 3n plus 1, 3n plus 4. And I swapped that line. So that means 15n plus 17. And that should be the answer. And that is the answer. Awesome. Awesome. But why? How did I get it wrong then? Let's see. I'm looking through my working right now. Minus 36. Minus 36n. Minus 48. They cancel out. Minus 36. You know, honestly, I really don't know. I really don't know. I don't know. I got it. No, I haven't. I haven't got it. No, I really don't know. 8 plus 3. Dude. Wait a second. I think I might have spot the other. Okay, so I got 5 over 3 plus 4 over 9n plus 12. 9n plus 3. Okay. Wait, no. Is it plus 4? Yeah. No, minus 36. Sorry. Minus 36. 36. Oh, this might be too small for you guys. Oh well, just zoom in. It's a high quality. Dude, that's really small. Oh man. I don't think I can zoom in like that. No, I can't. Okay. So, minus 36 over. With this, we want to simplify. So, 5 over 3 minus over 3n plus 4, 3n plus 1, 4 over... Wait, I'm so confused. No, that's minus. So that gives 5 over 3 plus 4 over 3n plus 1, 3n plus 4. Yeah, and that's what I have here. And then the next step is where I made the mistake, I think. So you get 5, 9n squared plus 3n plus 4 plus 12. 3 plus 12, 15. Huh. That's what I put. That's what I put, bro. That's what I put. Okay. 3n plus 1. What am I doing wrong? I don't understand. I don't understand what I'm doing wrong. I don't get it, man. I don't understand what I'm doing wrong. It's got to be a step before that. Or maybe it's because I did BIDMAS wrong. So this came from and I actually did the subtraction like this. But that's not how BIDMAS works. Because for example, let's say we did 5 minus 7 minus 3. If we did that instead, we would be doing 5 minus 4. So if we equated 5 minus 7 minus 3 without brackets, 5 minus 7 minus 2, so minus 2 minus 3 is minus 5. 5 minus 4 is not minus 5. So I did the BIDMAS wrong. Don't do that, guys. That's why I got it wrong. Okay. I have to multiply them all at the same time. That's weird. That's something weird about simplifying. Anyways. That flapjack tastes so nice, bro. Anyways. So, we have proved that n plus 1 squared minus, prove that that is equal to an n plus 1, where a is a constant to be found. So, the way that methods of differences works is you actually just use trial and error. So when I equals 1, we're doing the summation, by the way. So when I equals 1, we have 1 plus 1 all squared, which is 4, minus r minus 1, so 0 squared, so here 0. R equals 2, let's see what happens. I have a glue stick there, by the way. Put that way. When r equals 2, 2 plus 1 is 3, 3 all squared is 9, minus 2 minus 1 is 1, 1 squared is 1. So r equals 3, let's see what happens. 3 plus 1, 4, 4 squared, 16, minus 3 minus 2, 2 squared, 4. So we see that if we carried this on, so for example, r equals 4, we get 25 minus 9. Do you see the pattern that's happening here? So here we have a minus 0, which is nothing. This 4 cancels with this minus 4. This 9 cancels with this minus 9. And if we kept on going, this pattern would carry on. This would cancel with that. So this one is always left there, it looks like. 149, because the 1 would have to be there. So these would keep cancelling until you get, if we used r equals n, we'd get n plus 1 squared minus n minus 1 squared, where this would cancel out with this one, right? Yeah, just like 16 and 16. So here we have minus 1 because that sticks, and then what is this? This is n plus 1 squared, plus this is n minus 1 all squared. Simplify that. Minus 1 plus n squared plus 2n plus 1 plus, that's just minus 1 plus 1 is 0, so that's just n squared. So we have 2n squared plus 2n. Oh, so that's our answer then. 2n, n plus 1. And this is the subject that I said was difficult literally just 2 days ago. So I'm so glad I understand it. It's a simple topic. Let's check our answer. Oh my days, the line of working is literally 2 lines for a 4-mark question. So yeah, a equals 2. Let's do the next one. This is fun, man. I like being on my own. Alright. Also, I was discussing a collab with Ilya, the other guy who's supposed to be, who started his YouTube channel earlier, and he said he would actually want to do it. Inshallah, we will be able to do a PAT question together. 3 over You know, I don't really like this, but we'll do it anyway. I hate partial fractions here. 3r plus 1, 3r plus 4 equals an bn plus c. Okay. So, we need partial fractions of thing. So if we use partial fractions, this means we have a over 3r plus 1, so just something, and then b over 3r plus 4, basically just splitting up. So we multiply by 3r plus 1 and multiply by 3r plus 4 on both sides. So you get 3 equals a 3r plus 1. So that means, so when we try, we just pick an r value that will make one of these 0. So if we want a to be 0, or this whole term to be 0, for example, we choose an r value of minus 4 over 3. But if you want this entire thing to be 0 instead, we do minus 1 over 3. You see that? So, when r equals minus 4 over 3, 3 equals minus 4 plus 1, so minus 3b, which means b equals minus 1. When r equals minus 1 over 3, that means 3 equals minus 1 plus 4, which is 3a, so a equals 1. That means this all equals 1 and minus 1, like that. Make sure you don't swap those around because lots of people make that mistake. Okay, so now we have our methods of differences. Now we just use, brute force the values. So when r equals 1, 1 over 3r plus 1 is 4, minus 1 over 3 plus 4 is 7. When r equals 2, 1 over 7, minus 1 over 6 plus 4 is 11. Sorry, that's 10. What am I on about? This just goes like that. So these cancel out, leaving us with 1 over 4 minus 1 over 3n plus 4, because we're substituting n here. Like that. Okay. So now that we have that, we just need to rearrange it. So 3n plus 4 minus 4 over 4, 3n plus 4 equals 3n over 12n plus 16. So a equals 3, b equals 12, c equals 16. Hopefully. 3, 12, 16, 3, 12, 16. Bada boom, bada bash. Okay. I've never said that before. Hence or otherwise show that 2n this one looks a bit difficult. Okay. So we have, let's start on a new board. 3, 12, 16. So we have that just 3, 12, 16. Yeah, so we have this is equal to that. But now we want 2n, the summation up to 2n, starting from r equals n. So that's the same as going from 2n. Starting from 1 is the same as starting from 1 and doing the same thing, take away, going up to n minus 1 and doing the same thing. So now we just substitute. Okay, so for this one would be 3, 2n, 12, 2n plus 16 minus 3n minus 1, 12n minus 1 plus. Now we just rearrange. simplify. 24n plus 16 minus 3n minus 3, 12n minus 12 plus 16. Let's just simplify again. What does this become? You can divide, what's the highest common factor? 2. 2, right? No, it's 4. No, it's 2. 3n, 12n plus 4 minus 3n minus 12n plus 4. Let's simplify again. I like simplifying. 12 plus minus n minus 1, 4n plus. No, you can't simplify. What are you on about? Stop trying to simplify so much. Okay. So now the only thing we can do is multiply by each other. Wait, they're already over the same base. Huh? What? That's 8, bro. That's 8. What are you on about? What are you actually on about? I don't know. Okay. I don't know. Okay. 3n, 12n plus 4, 12n plus 8, 12n plus 4, minus 3n minus 3. Make sure to put a bracket when you're doing a minus, by the way, because it's so easy to like flip one of the signs or something like that. 36x squared. Minus 36 plus 24. Minus 36 plus 24 is minus 12. That gives you 144n squared. 96 plus 48. 96 plus 48. I'll need a calculator for that, just in case. You can make easy arithmetic mistakes, bro. 144n plus 32 equals. Oh, that cancels out. 12n minus. So it's literally just 24 over this, which is, what's the highest common factor between 24 and 32? Is it 8? Should be. What's 144 divided by 8? 18. 18n squared plus 18n plus 4. So is that in the thing they want? And they want us to factorize. Whoa! We did something wrong. We did something wrong. This a bit. Oh, you see? I didn't flip the signs correctly. So. Sorry about that. This is actually 24n minus 24 over 144n squared plus 144n plus 32 equals 3n minus n minus 1. 18n squared plus 18n plus 4. Now we factorize the bottom. Lucky my calculator can do that for me. 18, 18, 4 gives us 3n plus 1, 3n plus 1 and 3n plus 2. Well, of course, that just gives me the solution. So this is 9n squared. We want 18n squared, so the coefficient at the front is 2. Is that the answer? That's the answer. Let's go. And that was only 4 marks, so nothing to get too excited about. His workings are shown below. What is the error he made? This guy made an error. Okay, I'm going to show you the question. We're doing the one with the student error, that one. What is the error? Let's see. His workings are shown below. Explain the error that he made. Dude, it's not minusing. He must have done partial fractions wrong. What? Dude, what are you on about, bro? What is this guy on about? Let's try to do partial fractions on that then. 2r plus 1. 2r plus 1 over r plus 1. Let's do partial fractions with that. R plus b over. So as you remember, r plus 1 plus b r. So when r equals, what should we say, minus 1, minus 2 plus 1 is minus 1 equals minus b. b equals 1. When r equals 0, 1 equals a equals 1. So 1 over r plus 1 over r plus 1. What the? That's weird. How are you supposed to do methods of differences? If there's no cancellation that you can do. You guys understand what I'm talking about, right? So this is our equation for the summation of n equals r minus 1, like that. So if we substituted I equals 1, you would get 1 plus 1 over 2, and then 1 over 2 plus 1 over 3, etc. But nothing cancels out, as you can see. So when you sum them up, you will get 1 plus 2 times 1 over 2 plus 2 times 1 over 3. It will just be an infinite series, or like something like that. Wait, what is harmonic series? Harmonic series maths, what is that? Infinite series by positing all positive unit fractions. Interesting. Awesome. I think that's what you get here. Yeah, that's what you get here. It's something like the harmonic series, except the first value isn't multiplying by 2, and the last value isn't being multiplied by 2. So that should be the error, right? Terms don't cancel. Easy solution, bro. Alright, let's do one more question on methods of differences, and then that's called the end of the exercise. Okay, let's do question 12. Question 12 is, show that this plus 2 times 4 plus this up to 1 over n plus 2. I don't actually know how to do this. I guess I do. Okay. Oh, that's easy. Right, so that's just a summation of 1 over n plus 2, where the top equals n. How do I write that? Like that? Oh, you just write it without that. Okay. n, r equals 1, starting from 1. Okay, so when I equals 1, 1 over, oh, well, this is r plus 2. 1 over 3. We need a partial fraction set, that's why. And that's 6 marks, okay. Partial fractions, yay. I'm just going to assume it's this. Let's just check. So, r plus 2 minus r is 2 over r plus 2. So it needs to be a half. After partial fractions, I can't do it in my head. I hate partial fractions, man. 1 over r plus 2 equals 1 over r. A, B, r plus 2. So that means 1 equals a r plus 2 plus b r. When r equals minus 2, 1 equals minus 2b, so b is 1 over 2 minus. Okay. That means when r equals 0, 1 equals 2a, a equals 1 over 2. Alright. So this equals 1 over 2r minus 1 over 2r plus 4. So when r equals 1, that's 1 over 2 minus 1 over 6. When r equals 2, that's 1 over 4 minus 1 over 8. So these cancel out like this. When r equals 3, 1 over 6 minus 1 over 10. They cancel out like this. So we're left with 1 over 2 plus 1 over 4 minus, and this 1 over 2n plus 4. Okay, 1 over 2 plus 1 over 4 equals 3 over 4 minus 1 over 2n plus 4. Is that the answer? No, it's not. I forgot this term. Minus 1 over 2. More simplification, man. Okay, after I do this question, what was my lesson after this? I had computer science. Oh yeah, so computer science we were just working on an NEA. So I'm going to leave it at that. I'm going to finish this question and then I'm going to make wudu and then pray Maghrib and then cycle home, inshallah, so I can start working on my... So I can start working on my US applications because I'm so behind. I have to write 1,000 words in the next few days. I should have... Let's not talk about it, okay? Equals 3 over 4 minus 1 over 2n plus 4 minus 1 over 2n minus... So minus 2 plus... Wait. Don't have it. Minus 2 plus 4 is 2 plus 2. Remember, let's not do the same mistake as before. Can I write over here? Okay. 3, 2n plus 4, 2n plus 2, minus 4, 2n plus 2, minus 4, 2n plus 4. Man, I just crossed out my own working. 4, 2n plus 4, 2n plus 2 equals... Did you guys... there was a guy who commented on my video and he said, I would happily watch through a half an hour of you teaching your lessons throughout the day. And he would watch it again. But this is nearly 2 hours, okay? Who would want to watch 2 hours of someone like blabbering on about a subject they don't understand? Honestly, I don't understand. Anyways, that's just my thoughts right there. 8n plus 4n equals 12n plus 8 minus 8n minus 8 minus 8n minus 16 all over 4 2n plus 4 2n plus 2 equals 12n squared plus 36n plus 24 minus 8 minus 8 minus 8n minus 16 all over 4 2n plus 4 2n plus 2 equals 12n squared. Okay, 36 minus 16 is 20. 20n. 24 minus 8 minus 16 is 0. Okay, 4 2n plus 4 2n plus 2 equals, that's divisible. 12 and 4, there's a highest common factor of 4. So 3n squared plus 5n over 2n plus 4, 2n plus 2. I wonder if I sound cool, just blabbering numbers like that. It's 3n plus 5, 2n plus 4, 2n plus 2 should be the answer. So we have a equals 3, b equals 5, and then nah, please don't tell me I did it wrong. No. So if we simplify this, we get 3n squared plus 5n 4. Oh my. This is supposed to be easy, man. N plus 2, n plus 1. So that means, why would it be a fraction? That doesn't make sense. You're telling me a equals 3 over 4 on a fraction on the numerator, and b equals 5 over 4. And that means, there's no way. Oh wait, there's 2 at the bottom. So that means, this is 3 over 2. That's still a fraction. 5 over 2. There's no way. And I'm wrong. Oh. I simplified too much, man. So we started with this, but we want to collect this as one like term, which doesn't make sense. Because when I did it before, I got it wrong. Okay, let's try that. 3 over 4 minus 2n plus 2. Minus 2n plus 4. I think that was the problem. Okay, so plus. Wait a second. Okay. Minus 4n. 2n plus 4. 2n plus 2. That still doesn't give us the right answer. I don't know what I'm doing wrong. Wait, I think that does get us. No, it doesn't. It should though. But it doesn't. Oh. Okay, we're finally at the solution. Let me show you. So, all of this was unnecessary. If we bring this over here, I'm going to write this big for you guys once and for all. 3 over 4 plus minus 2n plus 2 minus 2n plus 4 equals 3 over 4 plus minus 4n. You know, I don't want to say it, but my answer's still wrong. And the thing that's wrong about it is that this is a plus. I don't know why that's a plus. Something's wrong here. Oh, I found out why. So instead of putting the minus there, you can do plus, minus, like that. So it's actually minus 2n minus 4, minus 2n minus 2, which gets us minus 4n minus 6, and 2n plus 3. And that concludes the end of today's video. I've only went through 3 lessons because, alhamdulillah, our last computer science lesson was just to do our NEA, so basically our coursework. We're not learning anything new. No joke, I'm 6 months behind on my NEA. We don't talk about it though. We don't talk about it. I'm gonna shut down my laptop. Yeah, I wanna go home as soon as possible. I'm gonna pray Maghrib. And then, when was Maghrib? Let me check my phone real quick. It says Maghrib was 7 minutes ago. Okay, I need to pray as soon as possible then. I hope you realize now look, I literally did a three A-levels worth of content just now, okay? And people think A-levels is easy. Imagine if I was doing 4 A-levels worth of content. I'd be here for at least another half an hour. Oh man. Okay. So yeah. I'd love to know how you guys are doing, because it's interesting to know other people's lives. Okay. Oh, I still have some of my flapjack left over. You know, even though I'm talking to a camera right now, I still don't want to like shut off the video because it feels like I'm actually with someone here. Maybe that just shows how lonely I am, or maybe think of everything positively, okay? Maybe that just shows how much like confidence and public speaking ability I've developed over time to be able to just like talk confidently like this, even when there's no one here. There's literally no one in this room. So yeah, it's a good thing. You should practice. My phone is probably 100%. I still 97%. Right, I'm gonna unplug my phone. Yeah, I don't want to end the video yet. I don't want to be left alone. And when I'm talking to you guys, I feel like I'm not alone. So that's pretty weird actually. So you guys are gonna pack up with me. Putting my charger in my bag. Right. Next is my pencil case, which does not have my glue stick inside, so I'm gonna put that inside right now. Okay. I mean, you know, these videos are actually just for myself. There's really no point in posting them, but like, oh, I nearly put my flapjack in the bin. Okay, I'm gonna put my laptop away. Oh yeah, I need to put my books away. There's a lot of them. Heavy too. My calculator. All these books, man. Look, I recently showed my friends that my bag was literally like empty on the inside, and it still weighed like like 6-7 kg. It was absolutely insane. And my bag is just so heavy, even though it looks like there's nothing inside. Okay, that's all my books. I'm gonna eat my flapjack now. But oh, my physics work is still here. You know, I might just put it in the bin because I don't want it. Dude, maybe that just shows that I'm attention seeking, that I want to be recorded all the time. Well, that's actually really creepy. The energy of the present. The energy of the present. Oh, that's so cool. Okay. Right, I'm gonna put this in the bin because I just read through it and it's no longer useful to me. I'm gonna finish my flapjack and then say goodbye. Right. All my stuff is put away apart from my prayer mat. I am going to say goodbye to you guys and then I'm going to make wudu and pray Maghrib as I said before. Oh. Okay, so that is the end of our study session. It was 2 hours, literally like non-stop 2 hours apart from eating some flapjacks. Like there's some people over there. I shouldn't have recorded them, that was not very good. So yeah, I moved all these chairs at the start of the session. But I need to play Maghrib. What am I doing? Stuff. So yeah, the sun is now gone. It's a lot darker in this room, that's why I had to turn the lights on. And yeah, I hope you enjoyed today's video. Inshallah, this will be one of many more videos in the upcoming future. You know, I really need a break. Assalamu